just going to jump straight into kinetics. And so before we talk about kinetics, we just need to briefly define what chemical kinetics are. So chemical kinetics just involve studying the rate of reactions. So how fast do reactions occur? How fast do reactants turn into products? And so the first thing we're going to do is talk about reaction mechanisms. So how we're going to do that is we're just going to kind of introduce this through an analogy. So let's imagine that we are just doing dishes, all right? So as we're doing dishes, what are we actually trying to accomplish? We are trying to turn a dirty dish into a clean and dry dish. Now, I could just say, oh, this is my reaction. I have a dirty dish and it becomes a clean and dry dish. But I don't just suddenly have a dirty dish and it just suddenly converts straight into a clean and dry dish. I can't just suddenly do one simple action and make it that way. Cleaning dishes involves multiple different steps, and that's what reaction mechanisms are all about. The steps that a chemical reaction must go through to actually end up as the final product. So, what is actually involved in doing dishes? Well, it's not just a dirty dish and then a clean dish. There's a number of different things you have to use, right? So some of those things include soap, water, a sponge, a towel, and then that'll convert the dirty dish into the clean dish. And like I said a second ago, I can't just throw all this at it at once and hope it magically becomes a clean dish. There's a step-by-step process, right? So I don't just take soap, put it on a sponge, wet it with a towel, and just throw that sloppy mess onto a dirty dish and say, ah, it's clean now. So the way that this is really going to work is in 3 steps for this example. So the first step is I have to wet the dish, and then I'll have a dirty, wet dish. Then after I wet the dish, I can use a sponge and soap and then make it a soapy clean dish. And then after I use the soapy clean dish, or I make the soapy clean dish, I can then just take a towel and then get that soapy clean dish nice and dry. And in the process of that, I also get the water off, as you might have seen. So in this process, multiple things occur, right? I have dirty dish plus water. I combine the two and I make a dirty wet dish. That dirty wet dish, I add a sponge and soap, and the soap is going to stay on the dirty wet dish, while the sponge I don't actually use anymore. It's not attached to the clean dish, so it's an entirely separate entity now. And now the soapy clean dish plus a towel equals a clean dry dish plus water plus towel plus soap. Now there are 3 steps here, right? Now, do all 3 of these steps occur at the same exact speed? Does it take me the same time to wet a dish, to clean a dish, and then dry a dish? Probably not, right? So let's just consider here. Let's say you have kind of a line of people working to do these tasks. So the first person is going to wet the dish. After they are done, they pass the task over to the next person who cleans the dish. And then as we move over to the last person, they dry the dish. Now this process, like we said, is not going to be equally spaced in time for step 1, step 2, and step 3. They're not all going to take, let's say, 10 seconds to do their job. Most likely, wetting the dish is not going to take very much time at all. I just have to put it under water. Drying the dish is just a simple rub on the top and the bottom of the dish. but cleaning it, scrubbing it, getting all of the dirt off is going to take a while. So this person would probably be finishing their task a lot and moving a lot of their plates over to this second person. And that second person is very slowly going to be able to give those plates over to the last person to finish off the task of cleaning dishes. And so, how long will it take to clean the dishes? The answer is however long this center person takes. And so, in this mechanism, we would call the task that that second person is tasked with to be the rate determining step. It's going to take the longest, and the overall rate of the process depends on the rate of that person's task. So, now that we're kind of done with that, let's just say real fast, what is the overall reaction here? So we know everything that we started with. We started with a dirty dish, soap, water, sponge, and towel, and we ended with a clean dish, soap, water, sponge, and another towel. So let's see. We're just going to look and see what's on the left side of this reaction, what's on the right side. So if there's something that appears on both the left and right side, we cancel it out. And we'll do that by looking at the actual mechanism here. So we have a dirty, wet dish and water. Water also occurs down here. So it's not used up in this reaction. I had it beforehand. I had it at the end. Big difference. We have a sponge on both sides. We have soap, we have a towel, we have a dirty wet dish, a clean wet dish, and soapy wet dish. Great, so everything's on both sides. So what was the overall reaction? Well, so the overall reaction is just going to be something that appears on the left side of the reaction and doesn't appear on the right side. And we'll figure that out by looking at the mechanism. So water appears on both sides, both the left and the right. The sponge does as well. The towel does. The soap does. And then the dirty wet dish does, as well as the soapy clean dish. So overall, the only thing that really changed here, or the overall reaction, is the dirty dish became a clean, dry dish. Now, of course, there are limitations to this example, but overall, it's a pretty good way of just understanding what a mechanism is and why it's important. So here, we can define what a reaction mechanism is. So a reaction mechanism is just the series of steps that a reaction must pass through to convert reactants to products. And we also said that the rate is how fast a given reaction takes place. So we also mentioned what rate determining step is, and so while the rate is how fast a given reaction takes place, the rate determining step decides the overall rate of the reaction based on what we call a slow step, which is which reaction takes the longest time to actually proceed. So rate determining step, also known as the slow step. Determines the rate of the overall reaction. A catalyst is some kind of substance. I'm not going to write this down. A catalyst is some kind of substance that is not used up in the mechanism. So I start with it, and at the same time, I end with it. So an example of that would be, let's say, the sponge. The sponge is something that I use in the actual chemical reaction, or you know what we call a chemical reaction here, but it's not actually going to incorporate or, let's say, be used up in the chemical reaction. That sponge is shown right here on the product side, and then it's never touched again. So it is a reactant and a product, while an intermediate is something that appears as a result of a chemical reaction and then is used up in the same chemical reaction. So a dirty, wet dish we did not start with. We used a dirty, wet dish, or we created a dirty, wet dish from adding water to our dirty dish. And then that dirty dish was then used up to create the soapy, clean dish. So it was an intermediate. It wasn't an original reactant, and it's not a final product. Yeah.